Hi everyone, welcome to our module on risk quantification. Let's talk about why risk is important. Much of our understanding of disease comes from estimation of risk. For example, we know that smoking increases the risk of lung cancer or that exercise decreases the risk of heart attacks. And by knowing these things, we can better advise patients how to avoid disease. And the reason we know these things is because we have techniques in epidemiology to quantify the risk. For example, we have ways to determine that smoking increases the risk of lung cancer by X%, or that exercise decreases the risk of heart attacks by Y%. So we obtain data for risk estimation by studying the presence or absence of risk factors or exposures in people with and without disease. And primarily, these data come from cohort and case control studies. And in another module on study design, I discuss in more detail the differences between these two types of epidemiology studies. So in order to understand risk quantification, we have to understand the 2 by 2 table. So when you get the results from a case control or a cohort study, they're typically put in a table like this. And along the top, we write the disease that we're studying, for example, lung cancer. And we put patients who have the disease over here on the left in this column labeled positive. And we put patients without the disease in this column on the right here that's labeled negative. And then on the side of it, we write exposure. So this might be exposure to smoking, for example. And patients who are exposed to smoking are written in the top row, and patients who are not exposed are written in the bottom row. So let me clear the screen here and just give you an example of how you use this table. So let's suppose we studied 100 patients, and 25 of them were exposed, so they'd be in the top row, and also had disease. Well, then we'd write the number 25 here. And then let's suppose we had another 30 patients who were exposed but did not have disease, then we'd write the number 30 right here. And you would do that for patients who are not exposed in the bottom two quadrants of the table. And this is how you create a 2 by 2 table, usually from a cohort or a case control study. So once you fill in the 2 by 2 table with the results of your study, you can use it to calculate many things. You can calculate the risk of disease, something called the risk ratio, and something called the odds ratio. You can calculate an attributable risk and a number needed to harm. And the ability to calculate all these things is very high yield for your boards. And in the rest of this module, we're going to go over how to estimate these things from a 2 by 2 table. So one very simple thing to calculate from a 2 by 2 table is the risk of disease in one group or another. So let's suppose we wanted to know the risk of disease in the exposed group. Well, we've got the disease up here, and let's say that this is lung cancer. So I'm just going to write LC. And let's suppose the exposure over here is smoking. So I'll just write SM. And among the patients who smoke right here, let's suppose that 25 of them had lung cancer. So we'd write 25 where the A is right there. And let's suppose 75 of them did not have lung cancer. Then we'd write 75 right there. This would mean that among the smokers, which is everybody in this top row, 25 out of 100 total patients had cancer. This means that the risk of cancer in patients exposed to smoking is 25 over 100, or 25%. And so you can do that for the top row to get the risk of disease in the exposed group. That would be A over A plus B. You can also do it in the bottom row here among the patients who weren't exposed to smoking and get the risk in the unexposed. That would be C over C plus D. And all we're doing here is taking the percentage of patients that are over here in the disease positive column as compared to the total in the entire row. Once you know the risk in the exposed and unexposed patients, you can calculate what's called a risk ratio. And to get this, you just divide the two numbers. So this is a risk of disease with exposure divided by the risk of disease with non-exposure. So let's suppose, for example, the risk ratio was 5 for smokers developing lung cancer. This means that smokers are 5 times more likely to get lung cancer than non-smokers, according to our study. Usually risk ratios come from a cohort study. We'll talk about why in a little bit. They're unreliable when you derive them from a case control study, except in certain special cases. And risk ratios range from 0 to infinity. So a risk ratio of 1 means there's no increased risk of disease if you're exposed. A risk ratio greater than 1 means exposure increases the risk. And if it's less than 1, it means exposure decreases the risk. This is sometimes called a protective exposure down here with the risk ratio less than 1. So let's go back to our 2 by 2 table and talk about how to calculate a risk ratio. So it's going to be the risk of disease among the exposed, which is the top row, divided by those unexposed, which is the bottom row. So the top row, it's going to be A divided by A plus B, and in the bottom row, it's going to be C divided by C plus D. So it's just a ratio of the two risks, top divided by bottom. Very easy to calculate. So let's go through some simple examples of how to interpret the risk ratio, because that's what you're often asked to do on exams. Let's suppose 10% of smokers get lung cancer and 10% of non-smokers get lung cancer. This means there's a risk ratio of 1, and it implies that smoking does not increase the risk of developing lung cancer. Now let's suppose 50% of smokers get lung cancer and 10% of non-smokers get lung cancer. Well, this would give you a risk ratio of 5, and like I talked about before, this means smokers are 5 times more likely to get lung cancer than non-smokers. Now let's suppose 10% of smokers get lung cancer and 50% of non-smokers get lung cancer. This would be a risk ratio of 0.2. This is less than 1, and it implies that smoking is protective. Obviously, this isn't true in reality, but I'm just giving you an example here. So now let's do something a little bit more complicated, which is to calculate a risk ratio based on a question stem. On the board, you're often given a question stem, and you have to fill in the 2x2 table yourself in order to use the equation for risk ratios. So let's do that now. So the question stem says a group of 1,000 college students is evaluated over 10 years. 200 are smokers and 800 are non-smokers. Over the 10-year study period, 50 smokers get lung cancer compared with 10 non-smokers. So let's start by focusing on this number 200. There were 200 smokers in the study. So I'm going to write that number right here because 200 is the total of patients in this quadrant and this quadrant. It's all the smokers in the study along the top. They also tell us that 800 patients are non-smokers, so I'm going to write the number 800 down here because 800 is the sum of these two quadrants. It's non-smokers who get cancer and non-smokers who don't. Next, they tell us that 50 smokers get lung cancer, so that number 50 goes right here because this top left quadrant always includes exposed patients who got disease, and smokers who get lung cancer are exposed patients with disease. And then they tell us 10 non-smokers got cancer, so that number 10 goes down here. Now we still have two blank quadrants, this one and this one, but we can figure out those numbers by deducing them from the totals. So if there were a total of 200 smokers and 50 got cancer, that means 150 must have not gotten cancer. And if there were a total of 800 non-smokers and 10 got cancer, this means 790 must have been cancer-free. And now we filled in a table ourselves, and we can go ahead and just plug in the numbers to calculate the risk ratio. So now let's talk about a different metric called the odds ratio, and this is a metric that we usually determine from a case control study. And it's the odds of exposure among disease patients divided by the odds of exposure among patients with no disease. And it ranges from 0 to infinity, just like the risk ratio. And once again, an odds ratio of 1 means exposure is equal among patients with disease and no disease. An odds ratio greater than 1 means exposure is increased among patients with disease, and an odds ratio less than 1 means there's less exposure among patients with disease compared to no disease. So back to our 2x2 table, let's talk about how to calculate the odds ratio. So for an odds ratio, we're going to take patients with disease first, and we're going to divide the diseased patients who are exposed by the diseased patients who are unexposed. Then we're going to take that whole number and we're going to divide it by the non-diseased patients. We're going to take the exposed divided by the unexposed for non-disease. And then we're going to take the ratio of these two. So let's look down here. So we're going to take A divided by C and divide it by B divided by D. And some people like to remember it as AD over BC. I prefer to remember it this way because then you can just look at the two columns next to each other. It's this column divided by that column, always with the top divided by the bottom. And that's how I remember the equation for an odds ratio. So let's talk about the risk ratio versus the odds ratio. You should know that risk ratio is the preferred metric. It's very easy to understand. It tells you how much exposure increases risk. It's much better if we can say smoking increases the risk of lung cancer by a factor of 5. And that's what you can say after you know the risk ratio. So why not calculate the risk ratio in all studies? Well, the reason is because the risk ratio is not valid in case control studies. And the reason it's not valid is because the risk ratio will change depending on the number of cases you choose. In order to understand this better, let's go through an example. So suppose we want to do a case control study of lung cancer and smoking. And we begin by finding 100 cases of people who have lung cancer, and we match those with 200 controls who are similar people who do not have lung cancer. And let's look down here at this 2x2 table. So among the 100 cancer patients, it's split up 50-50 for smokers and non-smokers. So we have 50 non-smokers and 50 smokers. Among the 200 controls, we have many more non-smokers. So we have 50 smokers, but 150 non-smokers. So if you put all these numbers together and you calculate a risk ratio, you would see that the risk ratio is 2. So this suggests that smoking increases the risk of lung cancer by a factor of 2. Now let's repeat the study, but this time we find 200 cases of lung cancer and 200 controls who do not have lung cancer. Well, let's go down to the 2 by 2 table. Once again, the 200 cases of lung cancer are split up 50-50. So we've got 100 people who don't smoke and 100 people who do. Once again, the 200 controls are split up such that there are 50 smokers and 150 non-smokers. Well, now we go through the math again and calculate the risk ratio, and we get a different number of 1.6. So we have changed the risk ratio, not because anything changed about smoking or lung cancer, but simply because we selected more cases of lung cancer. And this is why the risk ratio is not valid for case control studies, because it will vary depending on how many cases of disease you identify for your study. The odds ratio, on the other hand, does not change with the case number. So let's look here on the left side of the screen. This is where I found 100 cases of lung cancer, and they're split up 50-50, and the 200 controls are split up 50 and 150. So if we calculate an odds ratio here, we get an odds ratio of 3. On the right side of the screen is the second example where I had 200 lung cancer cases. They're split up 50-50 so that we have 100 here and 100 here. The 200 controls are split up so that there's 50 there and 150 here. So even though the numbers have changed over here, when we calculate the odds ratio, again, we get 3. The odds ratio is maintained no matter how many cases relative to controls you choose. And that's why we use the odds ratio in case control studies, because it does not vary based on the number of patients we study. So just to summarize, because this is an important point that often comes up in board questions, the risk ratio is dependent on the number of cases and controls. So it's invalid to use the risk ratio in a case control study where you can choose the number of cases of disease that you're going to have. In case control studies, you must use the odds ratio for this reason. Now, I just told you that you can't calculate a risk ratio from a case control study, but now I'm going to tell you that there is one exception to that rule, and that's in rare diseases. And this is something called the rare disease assumption. So let's look a little more carefully at the odds ratio and risk ratio equation. So the equation for an odds ratio is A over C divided by B over D, which you can rearrange to be A times D over B times C, which I've written right up here. The equation for a risk ratio is A over A plus B and C over C plus D. But now let's imagine something. Let's imagine that B is very, very large, and let's imagine that A is very, very small. If that's the case, then we can just cross A out because it really doesn't matter. B is so much bigger than it. B is the most important number. And then the top would become A over B, as I've drawn right here. Now for the bottom part of the risk ratio equation, we've got C over C plus D. But let's imagine that D is very, very big and that C is very, very small. And if that's the case, we can cross out the C. And then the bottom of this equation becomes C over D. And so we can rearrange this, and we get that the risk ratio is equal to A times D over B plus C. And that is exactly the same as the odds ratio equation. So it turns out that the odds ratio and the risk ratio are the same when B is much, much greater than A and when D is much, much greater than C. So let's look back at our 2 by 2 table. So B is the number of exposed patients who do not have disease, and A is the number of exposed patients who do have disease. So B is going to be much, much greater than A if the disease is rare. Among exposed patients, for example, smokers, if cancer is relatively rare, then we're going to have a lot more patients over here who do not have cancer and relatively few over here who do have cancer. So B is much greater than A when the disease is rare. And it turns out D is much greater than C also when the disease is rare. So among non-exposed patients, for example, among non-smokers, if lung cancer is rare, then this number for D is going to be very, very high, and this number for C is going to be very, very low. So when the disease is rare, B is going to be much greater than A, and D is going to be much greater than C, and this means the odds ratio and risk ratio will be identical to one another. So the rare disease assumption says that you can calculate an odds ratio and use that as a risk ratio or vice versa if the disease is rare. This means most of the exposed and unexposed patients must have no disease, or another way to look at it is there have to be very few disease-positive cases among the exposed and unexposed. So the rare disease assumption allows us to use a case control study design to determine a risk ratio. Remember, case control studies are usually done to determine an odds ratio, but when the disease is rare, we can use them to determine a risk ratio. The commonly accepted definition of a rare disease is a prevalence under 10%. So if your study population has a disease prevalence of less than 10% of the subjects, then you can make the rare disease assumption. And this is very helpful because case control studies are easier to do and they're often cheaper and less expensive. But we don't like that odds ratio. It's a weak association. It's a clumsy number. we like to use the risk ratio, and we're able to do that when the disease is rare. So one classic way for this to come up in a board question is for there to be a description of a case control study with a risk ratio reported, and the question asks, is this valid? And your answer should be yes, if the disease is rare, because only in that circumstance would it be all right to report a risk ratio with a case control study design. Another number that is sometimes reported in epidemiology studies is something called the attributable risk. So suppose there's a 1% chance of lung cancer among non-smokers, but a 21% chance in smokers. This means the attributable risk to smoking is 20%. It's the difference between those two numbers. This represents the added risk of exposure to smoking. And we can calculate the attributable risk from our 2x2 table. So remember, I said that the risk of disease among exposed patients is A over A plus B. It's this top row with A divided by the total. The risk of disease among non-exposed is the bottom row. So that's C over C plus D. When we take the ratio of these two rows, we get the risk ratio. But if we subtract one from another, we get the attributable risk. So it's just the difference in risk between exposed and unexposed patients. There's a number related to the attributable risk called the attributable risk percentage. So this is equal to the risk in exposed patients minus the risk unexposed. And this is the same as the attributable risk, but then you divide it by the risk in exposed. And the nice thing about this number is it represents the percent of disease explained by the risk factor. So for example, if the ARP for smoking and lung cancer was 80%, this suggests that 80% of lung cancers are explained by smoking, and people like to report numbers like this. They're very easy for people to understand. Another nice thing about the attributable risk percentage is that it can be calculated directly from the risk ratio. I won't go through all the math to derive this equation because it's complex, but suffice it to say that the ARP is equal to the risk ratio minus 1 divided by the risk ratio. So once you know the risk ratio, you can very easily calculate the attributable risk percentage. And then, as I said before, that's a number that's easy for people to understand because it tells you how much of the disease is explained by that risk factor. Sometimes instead of attributable risk, a different number is reported called the number needed to harm. This number is related to the attributable risk, but it's different. The number needed to harm is the number of patients on average that need to be exposed for one episode of disease on average to occur. So for example, it's the average number of people who need to smoke for one case of lung cancer to develop. And this is calculated from the attributable risk by the equation shown on the screen here. The number needed to harm is equal to 1 divided by the attributable risk. So if the AR for smoking was 20%, as in our previous example, then the number needed to harm is 1 over 20%, which is 5. And this is just an easier way to talk about risk. You can say that for every 5 people that smoke, one case of lung cancer develops. That's easier to get your mind around than an attributable risk of 20%. And that concludes our video on risk quantification.